So we've been talking about lots of different kinds of functions. We've talked about the absolute value graphs, which are these. We've talked about piecewise functions, and they can look like lots of different things because they're just different pieces put together. This is another kind of function that we need to talk about, and it's called polynomials. And there's some definitions and things that we'll talk about, but I want to go here in the middle and just let you see these graphs right here are called polynomial graphs. They're polynomial functions. They kind of go down and then up, or they might be up and then do some little things in the middle and then come back up. So all of these are polynomials. There's lots of different ways that polynomials can look, but that's the basic ways. Okay? So when we talk about what a polynomial is, it's many terms added or subtracted together. Now, there's one important part about that definition, and it's this part right here called terms. Okay? When I say terms right here, I'm talking about things that are raised to powers. For example, x squared, x to the third, x to the fourth, and so on. Okay? So, when we talk about polynomials, it's kind of like 2x squared minus 5x plus 10. It's several things that are added or subtracted together. The key is that these powers cannot be negative, and they can't be square roots. Okay? And so I'm going to write that note. No negative or square root powers. So when you're trying to determine, is this a polynomial or not, you're trying to figure out, am I adding a bunch of things together where the powers are just even or odd or positive, or do they have negative and square roots in them? Okay? So before we go on to the next definition, let's look down here on this 1 through 8. And I want to determine which of these are polynomials and which are not. Okay? I will tell you that number 1 is a polynomial. I'm just going to put a P beside of it, or maybe I'll write poly right there and just abbreviate it. Number 1 is a polynomial because we've got a squared, that's just an x, that's to the third, and that's just a number. That's just a bunch of things added, and there's no negatives, and there's no square roots. Okay, look at number 2. Here we have the power is a 3, the power is a negative 2, that's like a 1 power, and then a number. This one's not good. Number 2 is not good, and the reason is because we have a negative as the power. Okay, that can't happen. That's not a polynomial. So we don't even have to worry about that one when we answer some other questions we're going to look at here in a minute. On number 3, we've got a 4, we've got a 2, just a number, a 3, a 1. That one looks good. Nothing's weird about that one. Okay, look at the powers on number 4. We've got 2. There's a power of 1 here and then a number. You see that square root, but that square root's okay because it's not a power. Okay, as long as the power is okay. Okay, number 5. There's another negative here. That one's not a polynomial. When I look at the rest of them, number 6, number 7, and number 8, again I see a square root, but it's not a power, so that's okay. Same thing on 7. On 8, this one right here is the problem, 4 over x. Now, I don't see a negative power there, but there is a way that you can rewrite that to make it a negative power. It's 4x to the negative 1, and so this one is not a polynomial. The rest of these are polynomials because there's no negatives and no fractional powers. Now, our next definition, let's go back to the top. Our next definition said leading coefficient. Okay? Well, I'm going to do standard form and leading coefficient at the same time. Standard form is the form where it is put in order by power. The biggest power is first. Give you a few seconds to write that down. Once it is in standard form, the leading coefficient is the coefficient or the number at the start when it is in standard form. I'll show you what that means when we do some examples. But basically what that means is you have to put the polynomial in standard form, and once you have put it in standard form, then the coefficient is the number that's at the beginning. Okay? So let's look at a couple problems here. Let's scoot on back down to number 1. And let's put these things in standard form. Okay? And then when we do that, we're going to identify the leading coefficient. So if I put this in standard form, the one that comes first is the one with the biggest power. So 5x to the third is going to come first. Okay, next will be the second power, so 4x squared is going to come next. 3x will be next because that's to the first power. And then the number that doesn't have a power will always be at the end. Once it is in order like that, then we can tell that our leading coefficient is just the number at the beginning. So I'm going to abbreviate it with leading coefficient, LC, and that equals 5. Because number 2 is not a polynomial, we didn't have to do number 2, so we're just going to leave that one alone. Let's look at number 3. Alright, look at our powers. We got 4, 2, nothing, 3, and 1. So 4 has to come first. So we would have x to the 4th. Okay, then we're going to come on down to the one that has the third. The second one will be next. The one with just a 1, and then the number. And then again, we look at the beginning. There's an understood 1 here, and that will be our leading coefficient. If there's nothing there in front of the x, that's just understood to be a 1. Number 4 is already in standard form because it's 2, 1, and then no number. It's already in standard form, so that's nice. That means our leading coefficient is just 8. Number 6. Alright, we don't have to do 5 because it's not a polynomial. On 6, I do need to switch around these because I've got the second power, but then I need to go to the first power. So it's going to be 11x squared, the 12x, and then the square root of 7, because I'm always just looking at the x or the y and then the power. The number at the beginning is our leading coefficient, so our leading coefficient is 11. Got one more to look at. We don't have to do 8 because it's not a polynomial, but let's look at 7. On 7, we have the 4th power. Third would be here. Second here. First, and then number. So really the only thing we have to do is switch the middle 2. Make sure that you keep the sign with it when you switch it, because that's important. Again, the number at the beginning is our leading coefficient. So leading coefficient is 2. All right, let's look at the rest of these definitions real quick. So degree is the highest power. So once you have it in order, whatever power that comes first, that's the highest power, that's the degree. Okay? I'm going to go ahead and tell you some of these other definitions real quick, and then we're going to go back and finish the degree on those bottom ones. Zeros is where the graph crosses the x-axis. If it ever says how many zeros are there, you're just looking to see how many times the graph crosses the x-axis. And then the end behavior explains what happens on the end. And I'll explain that when we look at some examples there as well. Okay, very quickly, let's come back down to the bottom, and let's write down what these degrees are, just to make sure that we understand. So leading coefficient was the number at the beginning. The degree is the power, the highest power. So the highest power on number 1 was 3. So this time you're looking at the power that x is raised to. On number 3, the highest power is 4. On number 4, the highest power is 2. It's just that power at the beginning. Number 6, the highest power is 2. Number 7, the highest power is 4. And number 8 wasn't a polynomial. So degree is pretty easy after the things are in standard form and you just look for the highest power. Now, the degree and the leading coefficient affect the way the graph looks. So here's a bunch of different graphs. What you should know is that if the degree is odd, the graph is going to be this crazy, like, on one end it's down and on one end it's up. Or on one end it's up and on one end it's down. They're doing two different things on the ends. Okay? And that makes it be an odd degree. Alright? When they're doing the same thing on the ends, how they're both going up or both going down, that makes it have an even degree. So if you see a graph and it says, what degree is it? Look at the ends. If the ends are doing the same thing, then it's even. If the ends are doing opposite things, then it's odd. Now, to determine what the leading coefficient would be, basically whether it would be positive or negative, you kind of look again at the graph. This graph starts down here and goes up. It's kind of increasing, even though it kind of goes down a little bit. It starts down here and goes up. That's sort of increasing, which makes the leading coefficient be positive. This one, how it comes up here and then goes down, that one's sort of in a decreasing pattern. So its leading coefficient would be negative. These, I just think about the ends. They're both going up on the ends. So leading coefficient should be positive. This one's both going down on the ends, so leading coefficient should be negative. And you can, if you see some graphs and the question about the graphs, look back at this. This might help you to see the way the graph looks and then to determine what's going on. There's some notation here I want you to see as well. Talking about, it says, f of x approaches infinity as x approaches infinity. Sometimes with end behavior, they ask you questions like this. It says, what is f of x doing as x does this? Okay? Normally what it would mean, though, is it's going down and then up. Or up and then down. or up and then up. Okay? I'm going to show you some examples of that, and hopefully that will help you make more sense. The notation, I think, is the hardest part there. Okay? Let's look at some examples where we talk about all of that kind of stuff. So number 9 and number 10, it says describe the end behavior. Okay? So what I'm going to do is I'm going to graph it in Desmos. And good thing is that you can graph these, because these are going to be some weird graphs. So I'm just going to go ahead and put it in there. You can put g of x if you want to. It doesn't hurt anything to put that. Let's go back up there. I don't know what that was. I'm using the Shift 6 button to get those powers up there. But you can use this one right here that says a to the b. That will make those powers work for you. Alright, and so there's the graph. It doesn't look really strange. It kind of looks like a parabola. On the ends, which means like the top or the bottom, it's going up, right? The ends are going up. So one way to describe it is going up on both ends. Another thing that you could say is that the ends are going towards infinity. So they're both going up, they're both going towards infinity. Alright, so on the next one, negative 5x to the 9th, that's really weird, plus 6x to the 7th, minus 5x to the 4th, plus x squared, minus 1. Okay, here's that graph. Alrighty, so we've got something weird going on here. Okay, you see how it's up on the left and then down on the right? Okay, what that means, you could say up, then down. You could say it's going towards infinity, then negative infinity. Because if it's going up, it's going towards infinity. If it's going down, it's going towards negative infinity. Okay, let's look at 11 and 12. So this one is already graphed for us, so it's nice. I don't have to graph those. The first thing says describe the end behavior, and then there's some other things that ask. So what's number 11 doing? They're both going up. Or you could say infinity and then infinity, because we know they're both going towards infinity. Okay, let's look at this one. This one's opposite. Remember, start on the left. So on the left, it's going down, and then it's going up. So down and up. Down, and then up. So negative infinity, and then infinity. Alright, the degree tells me the shape of the graph. If it's up on both ends, the degree is even. If it's opposite, the degree is odd. So since it's up on both ends here, the degree is even. And since they're opposite here, the degree is odd. Leading coefficient, since they're both going up on that first one, the leading coefficient is positive. And this one's like starting down and then going up, kind of in an increasing pattern. So leading coefficient is positive again. Okay. So that chart from the front might be really, really helpful. The last thing we have is for us to compare the equations with the graph. And technically, we could just graph these in Desmos and compare them. Okay? But I think we can figure some of them out without having to do that. And that's what I want to show you real quick. So B, C, and F, they all have, like on the ends, they're doing the same thing. So that means that the degree is going to be even. The degree is going to be even. And the degree is going to be even on those three. Okay? So when I look down at my choices down here, C is even, D is even, and F is even because it's the highest power. Okay? Now, the other thing that's interesting about those three is this one's going down. Because it's going down, I know the leading coefficient is negative. So looking at those three, C has a leading coefficient that's negative, so little c has to be big B. Okay? Look at the other two, little c and little f. The only difference is this one has a little something going on there. Okay? When I compare these two, this is basic and this has something going on. Basic is going to be the big F, and something going on is the big C. Okay, let's look at the other three. These all have odd degrees because they're doing opposite things, and so these all have odd degrees. This one's kind of going up, this one's going up, this one's going down. This one's the different one. Because it's going down, I know the leading coefficient is negative, and the only one that has a leading coefficient being negative is this one. So that has to be D. And then lastly, A and E. Both of these are just going up, but this one has some stuff going on. That's got some stuff going on. So that has to be A, and this one has to be E.